So if you're missing these pages, it's not really a big deal. They're just meant to be a summary of everything that you've ever done in calculus, but you could just watch it from the video, or you can just jot it down on a scratch paper or something. So I thought it would be helpful to look at all of the types of integrals that we've dealt with in this class. So the first type of integral that you learned was in Calc 1, and it was this integral right here. This is your Calc 1 integral, and if you want an interpretation of it, it computes the area between the curve f of x, and I should say net area, the net area between f of x and the x-axis. Okay. Nothing new there, folks, but I just wanted to, this is what we're just kind of comparing and contrasting all of these. So then we learned in Calc 3, now we've learned this double integral here. Can everyone see that? This double integral here. And so it computes the net volume between f of xy and a region of the xy plane. I'm going to make a slight modification of what I said over here. I'm going to say it computes the net area between f of x and a region of the x-axis. Any questions on those first two? So this third integral, it really is too difficult for us to visualize, but it computes the volume, which we don't really have a word for, between f of x, y, z and the region E in R3. We don't have an interpretation, we don't have a word for volume. You could think of length as a one-dimensional volume. We've got length here. And then you could think of area as two-dimensional volume. And so then volume, as you normally use it, that's three-dimensional. And then you could just keep extending that upwards. You just keep crossing things with their dimension. I think that rather than think of this geometrically, I think the easiest avenue into understanding triple integrals is to think of your f as a density function. And so then this integral here would compute the total mass of that solid space. I think that's the easiest way to think of that type of problem. So you could think of this as computing mass of E, where you think of f as being a density function. That's just an interpretation that you give to it, folks. But that's a more accessible interpretation than talking about floor volume. So I would argue that almost all problems that we do beyond that, while we have different interpretations and different types of questions, almost all problems that we have beyond that are accomplished or solved or evaluated by converting them back into one of these ordinary integrals that we are more comfortable with. Okay? So all of these integrals, line integrals, regular line integrals, circulation integrals, flux integrals, surface integrals, flux surface integrals, flux curl integrals, all of those, when it comes time to evaluate them, we try to make them into one of these three. So what's an interpretation of this integral right here? I would interpret this integral right here, well, we're going to call it a line integral. And sometimes I put the word ordinary in front of it, just so I don't confuse it with the ones that have vectors in it. That's really my own construct. You don't need to do that. But let's call that an ordinary line integral. And the best interpretation I have for that is you could think of it as the mass of the curtain below f of x, y, z, or f, but let me just say below f, because that could be in any space, and the curve C. Let's add something there, folks. If f is 1, then that line integral computes the length of the curve. this integral computes this next integral computes the work done moving from A to B. So C is your path, and it computes the work done if you move the object from point A to point B. If closed, rather than calling it work, we prefer to call it circulation. So the easiest, if C is not closed, it doesn't really make sense to talk about circulation because you sort of have to have a closed loop for that concept to make sense. But if it's not closed, then rather you should think about moving an object through a force field, and the value of that line integral there gives you the amount of work it's required to move the object through the force field. So what about this next one, folks? Anytime you see an n vector in there, so what's our interpretation of that? It's a flux integral. Exactly. So this is a flux integral. And I'll just say that usually, if we're asking you to compute flux, we use a closed curve. I can't think of any example we've given you where we haven't had a closed curve for that. Now, you could still compute something like flux moving from A to B, but it's more ambiguous, one, because it's harder to talk about what your normal vector will be. If it's not closed, we can't talk about an outward pointing normal vector if it's not closed. Does that make sense, folks? What I just said is if you're moving from here to here, which way should the normal vector, here's your tangent vectors, so this is our direction, so your tangent vectors are going to be pointing in the direction of motion. Which way do your normal vectors go? Do they go this way, or do they go this way? Are they pointing this way or this way? And that's not clear if you don't have a closed loop. It's harder to specify what your normal vectors will be. Plus, generally we think of flux being across a small region. That just fits with the physical interpretations of, in physics or engineering, why would you want to compute this? Usually it's because you're talking about a closed interval. Okay? So flux versus circulation. Folks, I'm not going to review those now. I've reviewed them a few times. If you're not sure, you need to be sure of the difference between the two. Okay? So feel free to come by and see me. I'd love to help you with that. Go back and watch some of your earlier videos. All of those would be helpful. Even just YouTube, Google what is flux, what is circulation, and you'll get a lot of helpful information on that. But you have to know the difference between flux and circulation. So then here we have a surface area, a surface integral. And sometimes, because you compute these a little bit differently than the ones that have vectors in them, sometimes I'm going to put the word ordinary in front of that. An ordinary surface integral. If f is 1, then the double integral over s of f ds computes what? If f is 1, what does that surface integral compute, folks? Altogether, it computes the surface area. Everyone okay with that? A little concerned if you don't know that. You got to come by and see me because we got some catching up to do. Okay? It computes the surface area. Okay? So this integral here computes the flux across the surface. And if you wanted to, you could have said that this computed the flux and specifically outward flux. This is outward flux across the curve C. So they're both measuring like the degree to which the vectors in the vector field are moving perpendicular to whatever the object is. Okay? This one is a little bit harder to get a bead on, an interpretation on, but it's computing the, I'm going to say essentially, it's going to be the circulation along the surface. Let me not say circulation. That's because that's a little bit that's misleading. Let's say it's the rotation at each point along the surface. So total, say it like this: the total rotation on the surface. Really, what it's measuring, that's kind of a misleading statement. Really, what it's measuring is the degree to which the normal vectors on the surface point in the same direction as the rotational vector of the vector field. That's a lot harder to say, so I'll just say the total rotation on the surface. You can think of that, folks, if you want something more concrete, going along and at each point adding up how spinny the vector field is at each point along the surface. And by spinny, I mean things like eddies in the vector field that cause not flow in a direction, but rotation about axes. So it's like going along to every point on the surface and adding up how much of an eddy there is. If it's a big counterclockwise eddy based on the normal vector, then that gets a big number. And if it's not spinning at all, that gets 0. And if it's a big counterclockwise eddy and then relatively in alignment with your normal vector, then that gets counted as negative. Okay? That's all I want to say about it, other than to say it's kind of hard to specify an interpretation of that. Okay, as far as integral calculus goes, these are the integrals we've been doing in this course. And these are really the integrals you've been doing since Calc 1. You know, in Calc 2, you saw some parameterizations, you learned how to compute some arc length, you did some, you found areas of more complicated regions, but usually you were still working with just a variation of this integral here. And then we've got all of these other integrals that we've done in Calc 3. You can see why Calc 3 is a challenging course, because we so quickly expand upon the ideas you've been working on. Okay. I said this once before, let me say it one more time. These last 2 rows of integrals that we want to calculate them, to actually compute them, usually we convert them through a bunch of work to some version of one of these 3 integrals. The top row. So usually to compute any of these bottom 2 rows, to compute them, we rewrite them so that they look like one of these 3 integrals. And we're going to finish that idea out today. Okay? So then the question becomes, okay, now that we know what each one of these is asking, how do we compute each one of them? And for completion's sake, let's remind ourselves of how we compute the very first one. How do you compute this integral? You take f of b minus f of a. That's how everyone chooses to compute that integral. Folks, really, what are you supposed to do when you compute that integral? You're supposed to go to the limit definition of the Riemann sum, right? Nobody goes to the limit definition of the Riemann sum to evaluate that integral. And here we're saying that f is an antiderivative of little f. And what theorem am I using to make that statement, folks? It's pretty important to calculus. In fact, one would say it is fundamental, right? This was the fundamental theorem of calculus, part 2. For this one, what we will often do, and here I'm going to I'm just going to go ahead and write it this way, folks. I'm going to go ahead and write integral of the integral of f d something d something. I don't want to mislead you. I want this to be a very generic summary, and so I don't want to put x or y and assume that that'll always work. So this is, and here I'm not specifying these intervals on here, so I'm leaving that blank. But the point is, how did we learn how to evaluate a double integral, folks? We did it as an iterated integral. And you can't always evaluate a double integral as a iterated integral, but whenever a theorem called Fubini's theorem applied, then we were able to do so. And for all the functions we looked at in this class, Fubini's theorem applied. We didn't specifically, one way to mention this is we didn't integrate over regions of discontinuity. Okay? Folks, if what I just said about an iterated integral or Fubini's theorem, if what I just said about that doesn't ring a bell, that's okay. Go back and look it up after the class is over. What I'm saying is, whenever you go to evaluate a double integral, you break it up. And that's what we've been doing all along. So that's not a surprise, but we haven't phrased it that way since we first introduced the double integral. Frankly, then when we go to evaluate a triple integral, usually the way we evaluate it is this way. And again, I'm trying not to specify what that innermost variable is because I want this to remain general for you. But we basically work it back into a double integral, and then we evaluate the double integral the way we always evaluate it. Okay? So notice that all three of these integrals always end up going back to fundamental theorem of calculus part 1 or part 2, but the way we integrated in calculus 1. Okay, that was meant to be just kind of a feel-good review. Are we feeling okay with that? It's kind of funny to think that almost the first, we didn't get to this type of integral until we were 2/3 of the way through the class, and then in the last third of the class, we've covered all of these integrals. Right? It almost seems unfair, right, to go through and cover so many brand new concepts in the last little bit. The idea, though, is every time we're going to take one of these integrals in these 6 and break them down into one of those previous integrals. Either through directly applying a parameterization or by using one of our big theorems that greatly simplifies things for us. So if you're asked to evaluate this integral right here, you would evaluate it this way. You would do it from t equals a to t equals b of f of t times the magnitude of r prime of t dt, where c could be thought of in terms of the parameterization r of t for a less than or equal to t less than or equal to b. That's how you convert a line integral, which is what this is, to a Calc 1 integral. How are we doing, folks? I can't think of any shortcuts we could do for that unless you wanted to get into something called the arc length parameterization, which is something we briefly touched on. That would sometimes be a way of shortcutting this. But I can't think of another way to make the line integrals go any faster than that computation there, the ordinary line integrals. Where this starts to get more confusing now is in vector notation. And why this gets more confusing is partially because if you write out the full formula, it's complicated looking. And if you write out the simple, the condensed formula, you often miss what's going on. And math, to make sense to you, is finding the sweet spot between being overly pedantic with your formula and being too general with your formula. Which is why this class is sometimes so hard for folks, because everyone has to find their own sweet spot, which is not necessarily your instructor's sweet spot for describing these problems. And different authors write everything differently because they all have their own sweet spot for understanding how to do the computation. So the first thing I would say about this line integral here is that oftentimes we won't even write it that way, we'll just write it this way. In fact, more often than not, that's how we wrote it. That's already assuming that you've parameterized the curve, but not utilizing that parameterization in the calculation. So that was kind of confusion spot number 1 for these vector line integrals. By the way, let me just clarify something. I am making a distinction between what I call the ordinary line and surface integrals and the vector line and surface integrals, but there really isn't a difference, because notice that this never, through any of these computations, gives me a vector sitting underneath the integral signs, right? There's never a vector sitting under there, because once all is said and done with the vector calculations, you're always down to a regular function. Does everyone see that? Namely, all of those have eventually a dot product in them. And by the time when you do a dot product of vector functions, you're left with just a function. So there really is no difference in these problems, but it's a matter of interpretation. For all of these problems, we imagine our curves or our surfaces sitting inside of vector fields. That's how we choose to visualize it, as best as we're able to visualize it. Okay, so the next thing is okay, but how do we do a direct calculation of this? Generally, what we do is we go ahead and give a parameterization of our curve. And once we do that, we're able to write it as a Calc 1 integral. This would be f of, I'm just going to write t dotted with r prime of t dt. Folks, I could take that to one more granular level of simplicity. I could write it one more. In fact, let's see here. Let's go ahead and write that one other way. And I'm sorry to do this, folks. I'm going to move that down because I do want to show you this other version of circulation. The other way we sometimes write circulation is f dx plus g dy. Let me get that out of your. Just kind of smooth. But this is still no better for computation, right? It's just another way of phrasing the problem. I don't think that's any better for computation. How did we do a flux integral? I didn't have any other kind of vector way of writing a flux integral, but sometimes we would write it this way. We would write it as f dy minus g dx. That was another way of writing the flux integral. Notice the sort of unexpected ordering of the differential part. That's how you identify that that's a flux integral in this form. For those of you that are really thinking about this, there is no difference between a flux integral and a circulation integral as far as computation goes. It's just for the flux integral, you're using a different vector field than the vector field you were given. You just switch the components of the vector field around slightly, and then you do it the same way. If you'd like to talk more about that, let me know. But for the rest of us, what we're going to do is we're going to say, hey, that's a circulation integral, that's a flux integral. Okay. How do you compute a flux integral? We're going to do the integral from t equals a to t equals b. I'll just write f of t, y prime of t, minus g of t, x prime of t, dt. Okay. Where some of you have gotten into trouble with these types of notations, let me underline that in a different color. Where some of you have gotten in trouble with these types of notations is that you're not exactly sure where the y's and x's come from. They do not come from the vector field. They come from the parameterization. In this case, we'd be using, for both of these, r of t is equal to some x of t, y of t, if we're doing this in 2 dimensions. And so when you see a y prime of t, it's the derivative of the second component of your parameterization. If you want to evaluate this surface integral, we translate surface in. So notice that all 3 types of line integrals that we've looked at, we always transform them down to a ordinary Calc 1 single integral. All of our surface integrals, unless we're using some of our slick theorems, all of our surface integrals to do direct computation with, we transform them into a double integral. So this will be the double integral over r of f of uv times the magnitude of r sub u cross r sub v dA, where r sub uv parameterizes the surface S. So notice that essentially, unless you're using a slick theorem, folks, to evaluate any of these line integrals, you have to give the one-dimensional parameterization of the curve. Likewise, to evaluate any of these surface integrals, you have to give the two-dimensional parameterization of the surface, again, unless you're using a theorem that gets you away from doing a direct computation. So when we go to compute this is the double integral over R of f of uv dotted with the vector r sub u crossed r sub v. Again, where r of uv is a parameterization. Is everyone clear why this is considered a surface integral and this is considered a double integral? So what I'd like to point out is for these types of problems, we often had a curve, and rather than doing a problem with a curve, what we would do is we would do some ordinary line integral. So this would be the point A and B, and this would be the point T equals A and T equals B, and we would do a line integral of some function, we would do a regular integral of some function. This depended upon what exactly we were supposed to be computing over here. So when we talk about the line integral, this would be some c of f ds, and then this would be the integral from a to b of f of t magnitude r prime of t dt. So this thing right here is the function that we're finding the area beneath. That's as opposed to adding up and chopping up this curve into pieces. Nobody wants to chop up a curve into pieces in 3-space and add up little parts of it. Much easier to take us down to Calc 1 and just find the area underneath the curve of an equivalent function. Likewise, for here, when we're talking about integrating on a surface, it's very difficult to integrate over a surface. It involves breaking up the surface into little subsurfaces, somehow getting the area of that subsurface and multiplying that a representative point from within that, plugging a representative point from within that surface into your function, evaluating the function and multiplying it by the area of that little grid there. That is too hard, and so what we do instead is we bring it down into UV space, where our surface would now come from something like this, and we will generally, these will have come out to be nice and rectangular, and we'll work with this integral over here. So this would be the double integral over R of f of uv magnitude r sub u cross r sub v, if we were thinking about these for the ordinary integrals. So again, these are hard. We convert them to equivalent single and double integrals to evaluate them. I don't really have anything to add with this flux integral here, except to first of all say you would first, to do this, you could first compute its curl vector field, and then do the same thing that you did before. It would be the double integral over R of g of uv dotted with r sub u crossed r sub v dA. So what I have gone through, folks, in these images is all direct computations of the 6 integrals that we've been focusing on since we left chapter 16. Those are all the direct computations. Green's theorem gives us a handy way of converting this into a double integral, or a handy way of converting this into double integrals, which is a surprising way, which you might think, and I think is, a surprising way to tackle the problem. So Green's theorem gives us ways of converting those into double integrals. We'll make a little key with this. If I put that on there, we're going to say Green's helps. And if I put red on there, we're going to say Stokes helps. And then for this one here, which we haven't yet talked about, we're going to say the divergence theorem helps. In certain circumstances, it will help with those computations. I think we'll add just a little bit more. This is helpful or easier if conservative. So this one is also easier if the vector field is conservative. And surprisingly, we saw last time, so is this one. Because if the vector field is conservative, then its curl is 0. And then we'll just say, I'll say that this is easier if source free. Remember, source free meant that the divergence was 0. And so this was easier if the divergence was 0, and this was easier if the divergence is 0. We don't know why that is the case yet. We're going to see that today. I think that's the best I want to do. There may be a couple more things you could say. Notice that whenever I say easier if conservative, that means that the fundamental theorem of line integrals would apply to line integral questions. But I don't think I want to make the document any more cluttered. Let me say one other thing here. Notice there's 2 forms of Green's theorem. Green's theorem circulation form helps with the circulation question. Green's theorem flux form helps with the flux question. So folks, that is basically integral calculus. I guess there's more to learn beyond that, but that's everything we've talked about. Since Calc 1, that's integral calculus. Keep in mind, that you have to know both things. You have to know, when you answer questions, what on earth it is I'm asking you to compute. And that's sort of what I've put in this upper table. It's just the idea of what it is we're doing. Then you have to have a means of going through and calculating it. And in the table in green, I have filled out all of the... folks, I want to be a little bit careful here because I've used the just for your notes, I underlined something in red at one point, and I don't want you to confuse that with the key that I just gave. So in green, I gave you all of the ways of directly computing something, and then I've tried to, I shouldn't say directly computing, because, well, there's no one perfect chart you can make that's going to sum up all of calculus. If there was, I wouldn't be the one who made it. Somebody far smarter than me would have done that. So there is no chart that's going to summarize everything, but green is kind of the computation that you do directly. And then here you have some shortcut ways of working with them based on our various theorems.